Hello everyone, me Vakfali. So in this video I will walk through my solution for homework 2. So the purpose of this assignment is to reverse engineer a given ERM32 hexadecimal dump into assemble code and then logically reconstruct the behavior of the program. So let's start. The first step is converting each hexadecimal instruction from the given dump into its 32-bit binary representation. For example, this part, let me convert it to, yes, uh, we converted the hexadecimal number to the binary number. Actually, I don't want to lose time by converting each hexadecimal number to binary number because I have already converted all 15 hexadecimal number to the binary number. So let's move on. And after converting, we split uh, we split the binary number into the groups, which I am gonna explain it now. First of all, we need to define the. Let me check the. Yes, it will. First, we need to identify the operation code. There are three operation codes. First of all, let me check it. Yes. First of all is the data processing. The second one the memory access, and third one is branch. 00 is the data processing, 01 is the memory access, and 10 is the branch instruction. I'm gonna explain it. And then the first of all the data processing. It's our formula. It's our formula to this part. We split the 32-bit binary number into the groups. The condition operation I command is rnrd mt5 sh0rm. The operation code is the second one. It's located in 27th and 26th binary numbers, and our operation code is a 00, and that's we can define that it's data processing. It's just the example part. For example, this part's a command. It defines how to say the addition, subtraction. For example, let me check this one. For example, our command is equal to 0010. 0010 is the subtraction, and then we are looking at the subtraction one. For example, this part, the subtraction R5 is equal to R3 minus R4. And also this part, it's the same. It was just an example. I displayed as an example. And then memory access, the 01, and so formula condition operation I p u p w l r n r d and offset, and it's our example. I'm gonna explain it later. And also the last one, the branch 10, and condition operation l I m d d 24, and it's just our example. And then how to say, let's start with the data processing. Operation is equal to 0 0, and the condition 0 1 1 1 0, it's unconditional. And how to say 1 1 0 1, it's not, we can't see it in the table because it's just for defining the variables. For example, this part, the moving r1 is equal to 0, r2 is equal to 4, r3 is equal to 0, and r4 is equal to 5. It's just the how to identifying the variables, the constant variables. I mean, not all of them are constant actually. I'm gonna explain it later. Some of them are constant and one of them is a counter. Anyway, as you see, all of the hexadecimal numbers are converted to binary number, and they were split into the groups. And I is equal to 1. It is that one, this one, the third one. If I is equal to 1, it means it's immediate, and if I is equal to 0, it's a register. Let me show you this part. I is equal to 1, I is equal to 1, it's immediate. I is equal to 0, it's a register or register shifted. And then yes, and then memory access is it's here. As you see, operation code is equal to 0 1. Actually, we have only one memory access, it's this part, this hexadecimal number, and the condition 0 1, yes, and then we identify that I is equal to 0, P is equal to 0, U is equal to 0, P is equal to 0, W is equal to 1, L is equal to 0. And then we are gonna calculate it later. The branch is and the operation code is equal to 1 0. Let me check it. Yes, and the format is a condition 1 0. It's a branch. It identifies that the branch, the operation code is 1 0. Anyway, L and IMM 24, and then we calculated it as I mentioned before. Yes, here you go with the data processing. Because of the operation code is equal to 0 0, and immediate because I is equal to 1, and the command is equal to 1 1 0 1. It's just identifying the variables, and that's why the move r1 is 0, r2 is 10, r3 is equal to 0, and r4 is equal to 5. And for example, that one, it's the same actually. No, it's not the same. For example, I is equal to 0, and that's why it's a register. And 0 0 1 0, let me check it. Yes, 0 0 1 0, it's a subtraction. I'm the third one. That's why we use subtraction. R5 is equal to R3 minus R4, and 0 0 1 0 and 0 1 0 0 0 1 0 0 is the addition. We use it here. addition, r3 is equal to r3 plus 1, and also here r0 is equal to r0 plus r2, and also immediate conditional, and we are defining it by using the operation code command, and here you go, sorry, condition and also condition. Yes, we are defining the conditional or not. We are using the condition number, binary number. Oh, as a result, as you see, the condition, operation I, and command is the most important part. The other ones are also important, but we need to give more attention to the first four groups. And the memory access is 0, 1, because of being equal to 0, 1 for the operation code. This is 0, 1. Anyway, I is equal to 0, P 0, U 0, B 0, W 1, and L 0. Sorry for interruption. Yes, this one. And that part, actually, I know actually, but I want you to show you. Sorry, it was memory instruction. Yes. As you see, our I is equal to 0, and that's why I is equal to its immediate offset, and our U is equal to 0. It means that's subtract offset from base, and that's why we used immediate and subtract offset. And also if you remember that our P is equal to 0 and W is equal to 1, P0 W1 not supported, as you see. I mean this part, the second one, and that's why we use not supported. I'm gonna explain it on the code later. And also L is equal to 0, B is equal to 0, and this instructions is str, as you see, and that's why we use str. And also as you see, again, the data processing operation code 00, it is 1101. It's just identifying the variables, as I said before. This part, this part, the addition part. We are defining it by using the 0100, because what's the command? 01, sorry, 0, sorry, 0100 is addition, and that's why we use addition, as I said before. Yes, it's our calculation part. Let's move on to the program, how the program works. So let's start. So let's continue with the coding part. Before starting, I wanna show you that the operation code which you see it's exactly the same with the homework PDF. The dump file, it's our 15 hexadecimal numbers, and it's our operation code. I'm in this part. It's the same, exactly the same. You can check it. It's the first one, and the last one. F9. So let's start. First, move r0 is equal to r1 is equal to 0. It's a initialization, and move r2 is equal to 10. It's a constant value. R3 is equal to 0. It's a loop counter, and R4 is equal to 5. It's a load value 5 into R4. Here, for example, if we look into the loop, we see that subtraction R5 is equal to R0. Let's write it. R5 is equal to R3 minus R4. It means that if we know that R4 is equal to 5, we can it makes this condition, like if R3 is less than 5, then R0 is equal to R0 plus R2. R0 is equal to R0 plus R2, and as you know, R2 is equal to 10. 10, and then R3 is equal to R3 plus 1. You can do it like that. Yes. First, we are looking at R0 is equal to, we are starting from 0 because our initial value of the R0 is equal to 0. Plus, if R3 is less than 5, our R3 is equal to 0, and that's why 0 is less than 5, and that's why R0 plus 10, we write plus 10, and R3 is equal to R3 plus 1, it means 0 plus 1. 0 plus 1 is equal to 1, and again 1 is less than 5, and that's why plus 10 can write. And 1 plus 1 2, and 2 is less than 5, and plus 10, and 2 plus 1 is equal to 3, and 3 is less than 5, and that's why 1 more 10, and 3 plus 1 is equal to 4, and 4 is less than 5, and that's why 1 more plus 10, and 4 plus 1 is equal to 5, and 5 is not less than 5, and that's why the program this part the looping stops here. 1 2 3 4 5 times 5 times 10, which is equal to 50, and our R0 is equal to 50. Let's keep continue. let's sorry, yes, and it's our BLT loop. This instruction branches back to the loop level if the LT condition is still true. As I mentioned before, once less than 5 loops continue, 2 is less than 5 loops continue, 3 is less than 5 loops can keep continue again, 4 is less than 5 let's continue again, because this condition are true. And then BL function. This instruction branches to the function named function. At the same time, it stores the return address in the link register LR, and the function str LR and then bracket sb minus 4. This instruction decrements the stack pointer by 4 bytes and stores the link register on the stack. So this is the function prologue and indicates that the function intends to return later. And then move R4 is equal to 15. This instruction loads the value 15 into register R4, and this value is used for arithmetic inside the function. And R5 is equal to 10. This instruction loads the value 10 into the register R5, and addition R6 is equal to R5 plus R4, and this instruction adds R5 and R4 together and stores the result, which is 25. I mean the 15 plus 10. It is they are our local variables, not the global. This operation doesn't affect program control flow actually, because there is no, you can't say anything about R5, sorry, R6, and subtraction R5 is equal to R3 minus R4, and this instruction subtract R4 from R3 and updates the condition flags. However, the flags set here are not used by any conditional instruction afterward. And B function. This instruction unconditionally branches back to the start of the function. Because of this, the function never returns. So the saved return address is never restored, creating an infinite loop. As a result, the main loop executes correctly and terminates, but the function contains an unconditional branch to itself. This causes infinite execution and explains why the program hangs or crashes. So that's all about the programming part, and it's our the logical reconstruction of the program in readme md. Everything is as I explained, and it's our ss. That's all about the assignment. Thank you for your attention.